All right. Hello, everyone. My name's Nico, and I'm going to be hosting a review session for 123A for all of you guys. I'll say again before we get started, if anyone has any questions, feel free to just jump in. And if you guys want to switch to some material that is not the questions that I have going on, you can bring up your own questions and I'll do my best to go through them on the spot. I definitely want to, I'm going to try to use this as more like an office hour for you guys, or, technically like 2 hours of office hours for you guys. But I do have some questions prepared. So if you guys would rather just go through those, I'll just start going through those. So anything? No? Cool. I will go ahead and start sharing my screen then. So let's see, I'll go ahead and go with this. All right, can you guys see my screen right now?
Yeah, we can see it.
Great. Wonderful. Give me a second to get set up here. All right. So one of the main concepts in this, and I think one of the first things I saw on the syllabus there was Bohr's atom. So if you don't remember the four ideas of Bohr's model, I can list those out. But this first question is going to be essentially surrounding that. So the idea is first that using Bohr's model, you derive the energy levels of the hydrogen atom. This is something that you probably did in class. And then after that, you're just going to simply find the energy between the ground state and the second excited state. And then the Bohr radius is seen as the radius of the hydrogen atom, or the distance from the nucleus to the electron in the hydrogen atom. And then the idea would be to find an expression for that radius, specifically in the hydrogen atom. So before I set you guys off and let you guys start thinking about this, does anyone have any questions about this problem? If you'd like, I can show you guys what the four rules of Bohr models are. Bohr's model is, but it might be best to either find those in your notes, or if you have a cheat sheet that you're going to use on the test, maybe try to, write those down. All right, cool. So go ahead and get started on this problem. If you have questions while you're doing the problem, let me know and I will do my best to answer them. All right, did everyone get a good chance to take a crack at this one? You guys want a little more time?
Oh yeah, just a bit for me.
Okay. Well. All right. So like another 5 minutes, I should say, because this is a question that came up in the last review session. I'm not pacing this at any pace that you should be going at, or I don't know what the test is going to look like. But these should be like, as soon as you see these questions, you should have a pretty good idea of how to approach them. So if off the bat you don't see how to approach them, then the explanations will probably be a little more beneficial for them. So yeah, I'll give you guys another like 5 minutes. All right, let's go ahead and get started with this first one. So, around some things here real quick. Okay, just making sure. We got 2 monitors going on, lots of fancy equipment, gotta make sure it's all working. All right, so to start with, we want to use Bohr's model to derive the energy of the hydrogen atom. So I'll go ahead and start with stating what the 4 tenets rules of Bohr's model are. So this is for A. So to start with, we have that the electron revolves around the nucleus in a circular orbit, right? This was something that Bohr was like, yeah, it seems pretty clear. Revolves around nucleus. And I'll just put circular here because he did specify it was a circular orbit. The second thing is that the angular momentum of the electron is quantized, or quite simply that L, which is the angular momentum, is some integer times h bar. So I'll say also for all you math folks out there that n is an integer. I guess technically an integer, a positive integer. And then lastly, second to last, is that it doesn't emit radiation as it's moving around this, right? So one of the classical issues was that you had this nucleus and the idea of an electron spinning around it, right? You're like, it's accelerating technically. So wouldn't it be emitting photons? So as it's emitting photons, wouldn't it then lose energy and then fall closer and closer into the nucleus of the atom, and then all of a sudden they would just combine with the proton? Well, it's sort of the idea there is that, now one of Bohr's tenets is that it can't do that, right? So it doesn't emit any photons as it's orbiting around the nucleus. So no emission of photons while orbiting. And the last thing is that it does emit photons or absorb photons, if you look at the other way, when it's jumping between states. So emission, well, I'll just say while jumping. So with these 4 things, Bohr is actually able to derive a very, very, very good model, actually the exact equation for the energies in a hydrogen atom. So let's think a little bit about how he did that. So with the first thing, this first rule he had. So the electron revolves around the nucleus. All right, well, we know that the, we know the potential for the electron at a particular, sorry, not the potential, the force, the centripetal force that the electron feels while orbiting around the nucleus is given by this equation, right? Just the Coulomb force. And in this case, E is, or I should, no, this is actually the potential. Sorry, my bad. The potential is given by this. And Z here is just the number, is the number of the nucleus, right? So Z is 2 when there are 2 protons, 3 when there are 3 protons, so on and so forth. And we know that this potential is equal to mv squared over r. That is to say that this potential is equal to a centripetal potential, right? And you should remember that from your physics 1A, right? Second thing is simply that, L is nh bar, but that this is also equal to mvr. Yes. So that means that, let's see what exactly, yeah. So we're gonna change this out for V, because V is gonna be something that we end up wanting to have a different equation for. So we say that V is then equal to nh bar over mr. Okay, any questions so far? Seems like it's pretty straightforward stuff. This is really just sort of, if you were to be given this problem, how would you approach it? Well, you did the derivation in class, so hopefully maybe remember that. But the other way to do it would be to sort of, start writing off things you know. You know, for example, that if the electron revolves around the nucleus, that whatever the potential is, that must be equal to a centripetal potential, right? You know that if L equals n times h bar, then maybe it would be more beneficial to put that into units you understand, which is mass times, or momentum times radius, which is the units of angular momentum, right? Okay, so next up, we can then just look at the actual potential for this, right? Or the actual force for this. So we have that, we'll just write this out next. 4 pi epsilon naught r squared. So we know that this is equal to n squared h bar squared over m r cubed. Oh shoot, this should be a squared. I was right. I should have trusted myself on that. I was thinking that is the force. But so where do we get this from? Well, I just took this v and I plugged it into there. And I just combined those two equations. So what this gives us is that r is equal to 4 pi epsilon naught over z e squared times n squared h bar squared over m. Okay. So we have the radius in general for what this system is going to look like, right? So this is what the radius of the electron's orbit would be around the atom. We also, though, know that we can use this to actually solve for v more explicitly, right? And I'll just go ahead and write that out. And that is just going to be that v is z e squared over 4 pi epsilon naught times 1 over n h bar. So really just dividing out mr, right? Or taking r and manipulating it around so that we just get v. Yeah, that's it. Okay, so now with these two things, now comes the hard part. The idea is that we know what the velocity is, we know what the radius is, and from here we want to figure out what the total energy of an electron is, right? And the electron energy is going to be pretty straightforward. It's just going to be its kinetic energy plus its potential energy. So we'll start with that. And K is the kinetic, and this is the potential. So the question is, what are these things, right? What exactly, what exactly are the values of these things? Well, we know that first of all, we know what the potential is, right? If we actually do the integral for this, if you want to, you might just know it, but you could also do the integral. So we know this is just the integral from 0 to infinity, from r to infinity of this value right here, what our force was, right? Or technically our potential field, z e squared over r squared, should be a squared, dr. And so this is just going to be equal to negative 1 over 4 pi epsilon naught z e squared over r, right? That's our potential field. Pretty straightforward. But now the question is, what is our kinetic energy? Well, we have what our kinetic energy is actually because we have, let's see, how do we have our kinetic energy? Well, because we have this right here. We have this guy right here. So, hold on. Right, we have what our kinetic energy is because, oh, geez. It should be this. It should essentially be half of the potential energy. And I just want to make sure I have a good explanation of where that comes from. Oh, right, because it's 1/2 mv squared, right? Which if you plug it into this equation up here, you'll just get the 1/2 from that. So if E tot equals K plus V, so if you notice, actually, here, I'll first point this out. Actually, it looks like 2 people have entered the waiting room. Let me go ahead and bring those people in. Okay. So if you notice right here, this is actually the exact same equation for this, only halved. So we can actually just say that the total energy is half the potential energy, right? And so that is actually just going to be negative ze squared over 4 pi epsilon naught r. 8 pi epsilon naught r. Okay. Very cool, very nice. From here, we just plug in r and we get what our energy is. So this means that E total, and I'm just going to do the math really quickly, is negative mz squared e to the fourth over 4 pi e naught squared 2 h bar squared n squared. And that is our result for energies of Bohr's atom. This should look very familiar. If we simplify this down to the case of the hydrogen atom, we just get that E total is equal to, I'm just essentially making Z equal to 1. And then this is 4 pi E naught squared 2 h bar squared n squared. Okay, pretty good stuff. So the next question asked, find the energy needed to bring the electron from the ground state to the second excited state, right? Well, the ground state is just the n equals 1 state, but the second excited state, and this is sort of tricky wording here. First excited state would be n equals 2. Second excited state would be n equals 3. So what that really means is that we're just going to plug in E for n equals 3 and subtract off E for n equals 1, right? And this is going to be equal to, let's see, this is going to be equal to what I will call E naught over 9 minus E naught. Technically negative E naught plus E naught. And this is going to be 8/9 of E naught, where E naught is equal to m e to the fourth over 4 pi epsilon naught squared 2 h bar squared. Hopefully my handwriting is at least slightly legible. Again, this should all be very straightforward stuff. Yep, and that is technically, this should be 13.6 electron volts. And then obviously, the famous number 13.6, negative 13.6 is the actual potential, but because of how I did my signs, that's just how this one's going to go. So this should be the amount for B. And then C asks, the Bohr radius, often denoted A, is seen as the radius of the hydrogen atom, or the distance from the nucleus to the electron in the hydrogen atom. Find an expression for A. So this is in particular in the hydrogen atom. But luckily, we already found an expression for the radius here. So I'm just going to take this and say R at Z equals 1, N equals 1, right? So in the ground state, the classical radius of the hydrogen atom. And that's just going to be this guy right here. 4 pi epsilon naught h bar squared over me squared. And that is your Bohr radius. All right. First question done. Any comments there? Anything anyone wants to ask about? Conceptual questions, things that are still a little confusing. Great. Let's go ahead and move on to the next question. All right. So next question is about the infinite square well potential. And it sort of goes a little bit into symmetric and anti-symmetric wave functions and fermions and bosons. I'll let you go ahead and read it, absorb it. Any questions off the bat? Just scanning over. Awesome. All right, I will let you guys get to it. We'll say, okay, it's 4:30 now, and I have a couple more questions. I will give you guys 10 minutes to do this one. That's definitely, you guys definitely have more time on the test. I just want to make sure that, if you guys at the end of it are like, we know how to do this one, you can skip it, then we can do that. Otherwise, I will let you guys get to it.
I have a question. Oh, you're muted. Sorry. So yeah, for 2A, so it says like, okay, splits this up equally between the ground and first excited states. Well, like I can create a wave equation for like the ground state and the first excited state, but then past that, I'm not sure what to do.
Like, how do you make an equation for the ground state and the first excited state?
Yeah, I think I read the textbook. I mean, I think in class we didn't even like talk about electrons splitting themselves between two states. But even then, like I read the textbook and I remember it saying that like you can only like split it between two states if like you use the time dependent one, not the time independent one.
Yeah. So you can still split it into two states. In theory, the idea would be that, like, quote, split itself equally into two states. What does that
Yeah.
mean? I guess I probably should have been more clear with that. Um, I'll give a note here. So it's equally likely to be in either state. That would
Okay.
be the proper way to think about that. So equal likelihood in states 1 and 2. Yeah, that's a good point though, because I could also say it splits its energy up equally into both states. Although that doesn't really have a good. There's not really a good way to do that, but it's better to be explicit. But the idea there would be that if you were to determine its state, then the probability of it being in state 1 would be 1/2, and the probability of it being in state 2 would be 1/2.
Okay.
Does that make more sense?
Yeah, I think it does.
Okay. Do you know how to go about doing that? If not, we'll wait a bit, but that's sort of the idea of that.
No, to be honest, I like past just writing down the way the equations for both states. I'm not sure what to do after that.
Sure. Yeah, I'll go through that. If you didn't cover anything like that though, it probably won't be on the test.
Yeah, we didn't cover anything like that, so yeah,
Okay.
that's fine.
Yeah.
Yeah.
I'll go through it quickly. Don't worry. Okay. Based on what you said, Houston, I think I'm just gonna start to go through it, just so that I can get through this. So first of all, finding the states of finding the ground state and the excited states, or just generally all states of the electron in this infinite potential well. This should also look like a familiar problem. Probably went through it in lecture. I wouldn't doubt it. But the idea is that you want to satisfy the boundary conditions, and then you also want to satisfy the Schrodinger equation. So I'll start with the Schrodinger equation, or I'll start with the Hamiltonian, which is negative h bar squared over 2m of the second derivative, technically the full derivative, because this is just in this is just inside the well. So the Hamiltonian is negative h bar squared over 2m plus the second derivative of psi with respect to x plus 0. And that is because, or I should say, and this is for 0 less than x less than L, and then we don't really have to worry about it for the infinite case because, well, it can't exist there because there's infinite potential and nothing can have infinite energy. At least that's a semi-pseudo-physicsy way to think about it. So the idea is then that if we have this equation, right, negative h bar squared over 2m d squared psi by dx squared is equal to, or I should say that this is h psi, right, is equal to our energy values times psi, right? And then you do your standard thing where you say, okay, that means that second derivative of psi with respect to x squared is equal to, let's see, negative 2me over h bar squared. H bar squared psi. So if we say k equals the square root of 2me over h bar, you guys have seen these solutions before. These are solutions for sines and cosines. Wonderful. So we know that psi is equal to some sine A sine of kx plus b cosine of kx. Wonderful. Great. But the question is, what are these solutions? Well, that's when we start plugging in boundary conditions. So we know that at 0 and at infinity, at 0 and at L, these have to go to 0, right? That's just, this equation has to go to 0. And that will immediately say that, so I'll say since psi at L equals 0, we know that B equals 0, right? That's the standard thing, that these have to be signed solutions because, there's no way to satisfy both at the same time. I guess technically the first step would be that we say that psi at 0, let's see. Right, that psi at 0 equals 0. And then saying that psi at L equals 0 means that that we get this periodic potential, right? That n pi has to be equal to KL. So that just means that K equals n pi over L. Okay, and then the last step, someone want to give me what the last step is to finding what this is. There's one thing that we have left to find out. We know that psi, at this point, we know that psi is equal to a sine of n pi x over L. Any takers?
Do we need to solve for E? Or
for E?
Yeah, I mean to solve for E, right? Or
yeah, actually we do. We can. That is definitely not necessary to this particular problem, but it's definitely good to do to solve for E. I was thinking that we solve for A, which is at this point, unresolved. And how do we do that? Well, we say, I'll solve for E in a second, but the way that we solve for A is we say that the square of, so we say the magnitude squared of this guy has to be equal to 1, right? So we know there's a particle, so the probability of finding the particle somewhere is 1. And so what this would actually state, you can go through the mathematics, it would state that A equals the square root of 2 over L. Wait, let me actually go through that. I just want to make sure I have that right. It should be that, but I'm sort of just saying that based off of what I know, but I'll go through the mathematics so I don't doubt myself. So this is actually the integral from 0 to L of this guy right here, a squared sine squared of n pi x over L. Whoop. And then we know that this right here is just going to be a squared times the integral from 0 to L of sine squared of n pi x over L dx. Forgot that. And that this is just going to be equal to a squared. And so I should mention that this right here is going to be the integral resolves to L over 2. So a squared times L over 2 equals 1. And this means that A equals root 2 over L. Okay. I'm going through this a bit quickly because I think you guys have all seen this before. And then I'll also just quickly say that the energy is equal to h bar squared k squared over 2m. And that is just equal to, well, we know what k is, we know it's n pi over L. So it's h bar squared n squared pi squared over 2ml squared. Okay. Any questions so far? No? Great. So we know that psi overall then, well, what we first know is we know that we have it half in one state and half in the other state. So the probability of finding it in the first state is 1/2, and the probability of finding it in the second state is 1/2, as the problem tells us, right? So how do we make a function that looks like that? Well, we're going to utilize the fact, I'll start with utilizing the fact that if we take the inner product of two of these, so let's say that I'm going to call our solution psi n is equal to root 2 over L sine of n pi x over L. And these are our solutions, right? And what we can do is we can note that, let me know if this notation doesn't look familiar. I am familiar with this notation being used in my class, but I understand if it's something that's not used in your class, and I can write it out differently.
Yeah, we did use this notation.
You didn't use this notation? Okay, that's fine. That's fine. So then I'll just write it like this. The way to think of these functions, these states, are as vectors. And the way that this algebra is sort of made up inside of this vector space is such that there is an orthonormal basis. So when you take the inner product of two of these vectors, the inner product being this operation right here, of psi n of x, psi m of x, well, they're orthonormal. So this is 0. If you remember taking 102, this is similar to how a Fourier series works, right? So essentially, because if we have psi of n and psi of m, then if n and m are not the same, then we have two sines of two different frequencies, which means when we take the integral over their period, they just resolve to 0. The only time that they don't resolve to 0 is when n is equal to m. So I guess more explicitly, I should write, some sort of split function where this is 1 when n is equal to m and 0 otherwise, right? So then we can really easily utilize that to make up this function that is the sum of these two, or that is evenly split between the first state and between the ground state and the first excited state. So with that, I will go ahead and I'll write out the solution, and then I'll show that's how it works. Or actually, I'll write out the solution. You can show to yourself later that's how it works, just so I'm not using too much time on it. So we know that psi overall of x is going to be equal to 1 over the square root of 2 times psi 1 of x times plus 1 over the square root of 2 psi 2 of x. And more explicitly, this would actually just be 1 over the square root of L times sine of, come on, there we go, pi x over L plus the sine of 2 pi x over L. All right. And that is our solution. So that is essentially saying that this electron is equally split between the first two states. Any questions there? Okay, cool. So the next question is, what is the average energy of the particle? What do we get if we measured its energy? All right. Does anyone want to give an answer to this? Because this is a little more qualitative. It's okay. Don't be shy. It's only quantum mechanics. All right, that's fine. So I'll go ahead and go through it. What is the average energy of the particle? Well, since it's half split in one and half split in the other, we can generally say that it's going to be half of the first, the expected energy, I should say, or what we call the expected energy of the system, is half of the first energy plus half of the second energy. Now, if you're a stickler for the mathematics, you can go ahead and go through and actually apply the energy operator, which in this case is just the Hamiltonian, to each of these states. And what you will find is that you actually get this exact answer. More explicitly, this is actually just going to be equal to h bar squared pi squared over 2m L squared times 1 plus 4 times 1/2. So this is just going to be 5/2 of this guy right here. We'll say, boop, like that. Okay, and that's the average energy, right? What we call the expected energy of the particle, right? When you take the energy operator and you apply it to this state, that's what you get. But that is different than what the measured energy would be. Because what would the measured energy be? Well, half the time when we measure this, we would get that its energy is the energy of the ground state. And the other half the time when we measure this, we would get that its energy is the energy of the first excited state. So there wouldn't be any way for us to get any energy between those. And that's sort of the idea of that question, is just to point out that discrepancy and remind you that we are working with quantum mechanics where things are weird and discrete. All right, the last question now. 2 more electrons enter the well and occupy the lowest possible states they can. What states do they occupy and why? Now, does anyone want to answer this question? I'll let you guys think about it for a little bit. And if anyone wants to answer, you can unmute yourself and chat out. Really? No one? Dang. You guys make me feel like I'm bombing in a comedy club right now. Come on. All right. Okay, so 2 more electrons enter the well and occupy the lowest possible state they can. What do we know about electrons? Well, we know they have spin 1/2. And we know that because they have spin 1/2, that, or we should say that we know that they're fermions. And because we know that they're fermions, then they have 2 spin states, right? They have spin up and spin down. So we know that they can feasibly, 2 electrons can be in the same state at the same time, right? So we know that feasibly 2 electrons could be in the ground state at the same time. But the weird thing here is that there's an electron that is occupying the ground state and the excited state sort of at the same time. What does that mean? Well, let's say we put another electron inside of this well. The first thing that the first electron's going to do is it's going to say, oh, perfect, there's an empty space in the ground state, right? If our first electron is spin up, the other electron will just go spin down, right? But then the other electron comes along and it's like, oh, shoot, there's some weird stuff happening here. So what it's going to do is it will also split its energy equally into half into the ground state and half into the excited state. So overall, what would happen is you would end up with, no matter what, 1 electron, 2 electrons in the ground state and 1 electron in the first excited state. And if you think about it, that is the lowest energy configuration that you could have with these 3 electrons. So despite the fact that we didn't start with the lowest energy configuration we could possibly have, we ended up with that because I set this requirement. If you have further questions about that, that is sort of a key concept, at least in understanding quantum mechanics in general. Do I think that you would ask a question like that? I don't know Professor D'Aiello personally. I know she admires quantum mechanics greatly and might ask something like this. But I don't think that necessarily it would be I think it would be something that's a more challenging question because it would require you to think a little bit more about what's going on here. So are there any questions with regards to that? All right, I will keep moving forward then. This question right here, I will not go through right now. That's going to be something for afterwards. It's essentially just quantum mechanics machinery. And I think that I'd rather spend a little more time on concepts right now. And then as soon as we've gone through all that and I've answered any questions you guys have, I'd be more than happy to, work through it with you guys. It really is just like strict mathematics, and then sort of getting results out of that. So let's go ahead and move to this guy. So for the ground state of an electron in the hydrogen atom. First of all, you guys did the hydrogen atom, right?
Yeah.
Great. Wonderful. So let me go ahead and actually get this guy for you, what the ground state is. I should have put this. This is often referred to as the 100 state. So psi 100 is this guy right here. Woo. Okay. So the first question is find the expected position, R, and the expectation value of R squared. And then also, the next question is what is the most likely value of R for the electron? As in, again, if you were to measure it, where would you most likely find it? All right, I'll let you guys go ahead and get to that. This one's a little easier. And as a result of that, mostly, again, I want to make sure I have time to answer questions afterwards. So go ahead and take till 5. And feel free to ask questions while you're chugging through it. All right. Hopefully this one didn't take too long. Again, just some pretty straightforward stuff. As a result of that, I think I'm actually just going to give you guys the answers to this one. So the idea here is just that, let's start with A. When we take R, we're just doing this operation. Technically, this integral would be over all volume of R, or psi 100 times R times psi 100. Technically, this would be the operation, right? And this would be R squared sine theta dr d theta d phi. And this right here, so the complex conjugate of this function is the same as itself. And on top of that, since we're not doing any matrix multiplication, it doesn't matter what order we multiply these things in. So this is actually just equal to 1 over pi a cubed times the integral from 0 to infinity of r cubed times e to the negative 2 r over a. And then this is dr. And then this, I'm just going to say, is the integral of d sigma, where sigma, or sorry, d omega, where omega is the solid angle, aka just that this integral right here is equal to this integral 0 to 2 pi, 0 to pi of sine theta d theta d phi is just 4 pi. And from there, we should get that the expected value of r is equal to a over 4. Similarly, looks like someone just said something. No, okay. Similarly, you can take the expected value of r squared, and you will get a squared over 8. All right. So the last part of this question, what is the most likely value of r for the electron? All right. Who wants to answer that question?
Wait, why is r squared a squared over 8 and not a squared over 16?
It could be. I may have messed up the algebra there. It should just be another. So the idea here is that if you have r cubed, right, you sort of are just continuously pulling that r out with integration by parts. And that just ends up being the operation of multiplying by a over 2. So it should just be that this r squared is just another multiplication of r, which is just another multiplication of a over 2.
Oh, okay, I see. Yeah, never mind.
Okay, did you get that too?
Yeah, I see where it goes through in the integral. Let's do that.
Okay, cool. Okay, anyone want to give the most likely value of r for this electron?
A.
Yep, perfect. Seems like you guys get this one. Okay, so now last thing is just a couple of somewhat of conceptual questions. Maybe you saw these on your homework. The especially famous one here is this question of if an electron were a classical solid sphere with radius given by that, and it has angular momentum given by its spin, that is to say its angular momentum is h bar 2, then how fast in meters per second must the electron be spinning? Second question is about why bands of allowed energies form in semiconductors. And then the last one is density of states. So did you guys go through density of states yet?
Not yet.
Okay, so you can ignore that last one. Did you guys go through, you said you went through like a periodic delta function?
Yeah, we were covering the wave functions up until free electrons of metals.
Okay. So that one is still, I guess, relevant. Did you guys go through the full derivation for a periodic delta function and how that works with the electrons in there?
Yeah.
We did? Okay. So I would state definitely still answer that question if you can. Definitely you can try to go for something conceptual with that. but usually the mathematics is the best way to describe that one. Yeah, just take a crack at the first one. Have you guys seen the first question before? Take that as a no.
Yeah, we haven't.
Oh, you have?
No, we haven't. We have not.
Oh,
Sorry.
okay, okay. All right, cool. In that case, you might, I mean, that's a pretty common question. I'm surprised you guys haven't seen it by now. Yeah, go ahead and fire away at that. Let me know if you guys have any questions. Maybe take another 5 minutes. It's really not that complicated. All right, let's go ahead and get started. So, where are my notes on this? Here we are. Okay. Okay, I realized I did not actually do the explicit calculation, but I do have the expression for this first guy. So, the idea is similar to before. We have that if we're going to take the angular momentum of something, then that is just going to be MVR. Or sorry, the angular momentum of something spinning around on itself, right? You know, I realize I actually did this problem wrong in my notes, but that's okay because I can do it right now. So the first step is going to be to find the angular momentum of something, of a sphere spinning around itself, right? This is a bit of integration. So I'll go ahead and see if I can do that on the spot. Sorry, guys. I realized that I wrote this wrong down in my notes. Okay, so we know that angular momentum of something is equal to mvr. If we assume that an electron is a solid sphere, then we know all its mass is going to be concentrated at its ends, right? So let's assume that the, oh, you know what, let's actually do not this one, but m omega r squared. Yes. Okay. Any questions about why I'm using this piece of angular, or this idea for angular momentum? Okay. We also know that the mass, if it was concentrated on just the edge of it, right, we could say that it's equal to some rho times 4 pi r squared. Or I should say RC squared. Any questions there? Okay, so we know the overall momentum is h bar over 2, but if we actually want to find the angular momentum, we're going to have to do some integrals. So we'll go ahead and get started with that. That is the integral from, well, actually, we just want to do the full volume integral of every individual piece of mass and its angular momentum. So this would be m over 4 pi rc squared times omega r squared. And then this is going to be multiplied by our volume, differential volume unit. Okay, so I think that the best way to do this is going to be in spherical coordinates, but the important thing to recognize is that this r right here is actually going to be distance from the z-axis. Which changes based off of, or actually this is a surface integral, sorry guys. Technically this is over a surface, dA. But that is still distance from the z-axis. Okay. So this is the integral from okay, integral from 0 to 2 pi times the integral from 0 to pi of m over 4 pi rc squared omega, and then some r prime squared times what our differential area unit is, which is going to be r squared sine theta where this is a constant, rc squared sine theta. d omega. Okay. Okay. I think actually because I don't have this prepared, I'm worried to do this without actually getting. I'm worried that I'm not gonna get this right. If we have more time towards the end, I can just go ahead and look up and make sure that I did it right before. But I think that this is the right way to do it. So from here, you'd solve for L, and you'd set L equal to h bar over 2, and then solve for omega, and omega would be the the rotational frequency, and you could multiply omega by RC to get the velocity at the very, very, like the equator of the sphere. And from there, you could actually solve the problem. But for the sake of time, I won't go through it right now, but I can go through it at the end. So for part B, yeah, I'll say this is equal to, yeah, that's fine, that's fine. Does anyone want to give an answer for part B? Okay, that's fine. So if you remember in the derivation, I'll start with the mathematical reasoning. And I'm sure that Professor Diallo went through this reasoning as well. But if you remember in the derivation, the last equation that you end up with is cosine of some Ka equals, let's see, I actually have it like right here. Don't want to be writing wrong stuff down. I don't expect you guys to have this memorized. I'm also gonna give a, I guess, an intuitive explanation for this particular problem. I do think it's a good idea to have some sort of, mathematical reasoning for it as well. Anyways, this was some cosine cap A plus some beta, some term before the sine. It was like a sine of Ka. It looks like. Oh, you know what? It looks like it was like a sinc function here. And the idea there is that if you were to say that this is some f of z, then this is equal to cosine of z plus beta sinc of z, something like this. And so you'd have some equation, like if you were to actually match up these two functions, then, or more importantly, if you would actually write what f of z is, right? If I were to say this is f of z and this is z, we'd get something that looks like this. We'd have this, and then it would go down, and it would slowly like start to come to a something like this. And then this right here is 1. So the idea there is just that, okay, so if this is what f of z looks like, and this is equal to some cosine function, then the only place that this has solutions is, in these regions right here, right? And so you sort of start to get that they're actually forming bands, right? Here and here, where you actually do have solutions. And in the places in between, there can't be solutions. So that's the mathematical reasoning for it. The more intuitive reasoning for it that was given to me by Professor Candler when I took this class is that you can think of the electrons like runners in a hurdles race, and that they sort of have these potentials that they're trying to dodge, right? And there's only certain speeds that you can run at to actually dodge those hurdles, right? You can't run at any speed you want to and not just plow through the hurdles, right? If you're running too quickly, or if you're running too slow, well, if you're running slow enough, you can just keep jumping over the hurdles however you want to. But after a certain point, you'll be running so slow that you won't actually be able to clear the hurdle when you jump, right? If you're running too quickly, though, what'll happen is you'll land too close to the next hurdle, and then you won't be able to, ready yourself to jump in time after that. So the electrons are sort of doing the same thing, only more or less because they're waves, you can think of it like constructive and destructive interference. So that's the idea there. And then part C, because you guys haven't gone through density of states yet, I will not answer. But as far as problems that I have that I would like to show you right now, I think that that is all from me. I'll answer some questions. I'll stay here and I'll answer some questions right now. But yeah, if you guys want to go through anything else, feel free to stick around. I do have that final problem. But I will go through that after I stop recording. So for those of you who are watching this after, good luck on your midterm, and hope that was helpful.